Yeah, good evening. Going to explain 01 knapsack problem under branch and bound method. We already have seen this knapsack problem earlier, right? So, what is the problem definition? It says that you are given n number of items with the weights W1, W2. Yeah. So W1, W2, W3 and up to Wn. N number of items are given and each item is associated with these weights, right? And also some profits. Sometimes it will be given as values. Okay. So each item is associated with the weights and the profits, right? And you are also given a knapsack. Okay. And the knapsack is given the capacity capital M. And what is the requirement? It is required to find out the subset of the items that fit in the knapsack. What is the main objective of this? To maximize the profit. That means you need to choose the items to be kept in the knapsack so that the profits associated with the items will be more than any other combination. So that is the main objective, right? And also there is a constraint for this. What is that constraint? The weight of the object chosen should not exceed the capacity of the knapsack, right? So whatever the items you are putting, each time whenever you are putting the item, so you need to add its weight to the previous item's weight. That means the total weight of all these items should not exceed whatever the capacity given of the knapsack. That is the main requirement of this. Okay, so we can state the problem statement as we need to maximize the profit. So P of I, that is I runs from 1 to n. Then why do we have this xi here? Because this xi says that whether ith item has been chosen or not. If you are choosing this ith item, so xi value will be 1, otherwise it will be 0. Okay, so that is maximize the summation of this profit pi into xi. Xi will be given as a solution vector. So if there are 4 items, so then if you are writing 1, so this will be the x vector, right? X array 1 0, then 1 0. If you are writing the solution vector like this, what does it mean? The first item has been selected, the second item is not selected, the third item is selected, and the last item is not selected. That means only 1 and 3 items will be selected. The total profit of all these items will be the sum of the weights of this first item and third item. Okay, so this is the problem definition. Okay, then how do you find out the solution for that? For that, it says that the all the items must be ordered in the decreasing order of descending order, decreasing order of profit to weight ratios. That means for every item, you need to find out the ratio of profit to weight. Okay, and you need to arrange all the items in terms of the decreasing order of Pi by Wi. Okay, so as this problem we are solving under this branch and bound, what you need to do is you need to find out the upper bound because it's a maximization problem, right? We are going to maximize the profit. So you need to find the upper bound. The problem which we had seen earlier, that was a lower bound problem, but this will be upper bound problem. So you need to find out the upper bound for this, right? How do you find the upper bound? In the beginning, in the initial state, the upper bound, the upper bound, there is a formula for that. What is that formula? Upper bound is V. So now V is nothing but the profit, right? Value or profit are the same, right? And M is the capacity of the knapsack and W is the weight of the item. Then this is the ratio of the next item's value by Wi. Okay, so this you'll understand when you go through that example, right? Okay, so this is the formula for that. Okay. So now let us take one example and solve this under this branch and bound. So it is given the example is given in this way. So here you are given the item number and the weight and the value, and also VI by WI, value by weight it is given. And also all these items are sorted in the order of decreasing order of VI by WI. Sometimes if you are given a problem and if it is not only if you, sometimes you may be given only the knapsack's capacity, item, weight and value, but you need to arrange all the items in terms of decreasing order. But here in this question directly it is given value by weight, and also all the items have been arranged in the descending orders of value by weight. Okay, the capacity, the knapsack capacity is given as m is equal to 10, right? So this is a problem. So how do you go about it? First, as you know that the backtracking problems and branch and bound problems both can be solved by using this state space tree. Okay, so state space tree means obviously it'll be having the root, right? Then each node in the tree will be divided into two parts. In the upper part you're going to write the weight as well as the value or profit. Okay, so in this example we are taking the profit as a value only. So the value and the weight of the items will be given, and after that whatever the upper bound we are going to calculate in that state, we are going to give that, right? I repeat, each node is divided into two parts. The upper part will have the W and V values, and the lower part will have the upper bound. Okay, so then initial state, you know, like we are arriving at the root of the state space tree. In that, in the initially we take W is equal to 0, V is equal to 0 because we haven't selected any of the items. Okay, then initially you need to find out the upper bound. What is the upper bound formula? V. So here V, the value, plus my M minus W into VI plus 1 divided by VI plus 1, WI plus 1. So here I is equal to 0. That means we haven't selected any item yet, right? So here if you substitute the values in the upper bound formula V. So this is V. What is the value of the V? So here V comes here. V is equal to 0. Then after that M minus W. What is the value of M here? It is 10 minus. What is the value of the W here? 0. So 10 minus 0 is equal to 10. So V plus M minus W, which is nothing but 10. Okay. And VI by WI. VI plus 1 divided by WI plus. And what is the value of I here? It is 0. Then VI plus 1 divided by WI plus 1 will be V1 by W1. That means the weight divided by the value divided by weight ratio of the first item. So in this, what is the first value by weight of the first item? That is 10. So we are substituting in this formula. So we are getting 100 bound for this, as far as this upper bound of the initial state of the state space is concerned. That is, we have arrived at the root. So here when we write this, you have to make the root node. How do we make the root node? As I told you, the node will be divided into two parts. The first upper part we will write W is equal to 0 and V is equal to 0 because we haven't selected any item, and whatever the upper bound we had got by substituting the formula, we are getting that, right? Okay, next. So we go with the next item. That means we are going to consider the first item here. Okay, first item here. So as we have seen in the subset of items, the state space tree consists of, each node consists of two parts, two branches. The left branch is after inclusion of the item, the right branch is excluding that item. That means when you include so we are starting with the first item. So what will be the upper bound after considering? What will be the upper bound after considering the first item? That is, we'll make two parts here. First one is with that item 1 and without item 1. So the first item we are considering here. Okay, so this will come left, this will come to the right. Okay, so now what is the weight of the item if you are including the first item? Okay, so the previous item, what is the weight of the previous, like earlier, what is the weight? W is equal to 0. Now after including this first item, we need to consider the total weight must be Total weight must be the weight of the first item. What is the weight of the first item? 4. And total now till now what is the weight? 0. So total weight will be 4. Okay, in the same way, V is nothing but the value of the first item, which is 40, and the value of the previous one, because no, the all the weights and values will be being added on this path, right? Okay, so the previous weight as well as previous value will be added here. Previous weight and values will be 0 0 here, no? So that's why we are writing W is equal 4 and V is equal 40. Where are we getting this 4 and 40 from? This is the weight of the first item and this is the value of the first item. Okay, so after that we have to substitute in the formula. What is the formula? UB is equal to, okay, UB is equal to UB is equal to V plus M minus W into V2 by W2. Why V2 by W2? Because item I is equal to 1 here. So Vi plus 1 in the formula itself, Vi plus 1 divided by VWI plus 1. So that's where we are considering this, right? Okay, so what is the formula? V plus M minus W into V2 by W2. Okay, so here V is 40 plus M minus W is the weight, the total, the capacity of the knapsack, and what is the weight of the first item. So that is 6. So 6 V2 by W2 we will be having here itself, right? So that is nothing but the second item, sorry, V2 by second items, V2 by W value, 2 value. So that will be 6 here. Okay, so if you substitute that, you are getting the upper bound as 76. So this is when you include the item. What if you exclude that item? Without the item 1, what will be the upper bound? So here so far till now, I mean the previous weight was 0 and the value was 0. And now without the item, including the item means still we are not including the first item. So its weight becomes 0 and value becomes 0. So it will be remaining W is equal to 0 and V is equal to 0. And what is the value of M minus W? M is capacity is 10, but here W is the weight of the item, but we are not including that item. That's why we make it as 0. So what is the value of the M minus W? It is 10. So if you substitute here, you will be getting 60 here. So what are you going to do that? Here we are going to partially construct the partially we are going to construct the state space tree. So how do you construct? The first node we already had seen in the initial state, and here this node will have left child and right child. Right child means it is with 1 and the left child means it is with 1 and right child means it is without 1. Okay, so here with 1 W is equal to 4 and V is equal to 40. I mean here whatever the values we are getting W and V, we are going to write it, and whatever the upper bound we are considering, so that will be included here. And without 1, what are the values of W and V here? Okay, we are writing that. I'm sorry, here it is 0. It is 0. I'll make a correction in the notes, please. It is 0. Okay, and upper bound is equal to 60. Okay, and here next after that, because we are going to consider okay, let us number the do the numbering for the nodes, right? So this is 0, this is 1 and 2. Okay, so here in 1 and 2 nodes, we find that the upper bound of this is 76 and upper bound of this is 60. Because we are talking about the upper bound, obviously we will be choosing this particular node, that is 1. We are going to expand this node, right? Okay, so next what do? We have to take, okay, we have to consider the next item. What is that next item? So this is, sorry, I think it is, okay, yeah, next item is I is equal to 2 and here W3 by V3, because it is 2 I plus 1, Vi plus 1 and Wi plus 1 we need to write. So from the table it is 5. Okay, so we are considering the node 1 above, right? So I told you because the upper bound is more, we are going to expand this, right? And with item 2. So what is the weight of the second item? It is 7 in the table. Okay, and weight so far is 4. So what is the total weight? It is 11. But we have seen that The capacity of the the capacity of the knapsack is 10 only, but we are getting more weight, so this is not feasible. We will write not feasible. Okay, next what we will do without using the item 2. So the weight so far is 0, but if you consider this next item, its weight is 4. So what is the value you are getting? W is equal to 4, and value if you are considering, here also it is 0, please consider that as 0, 0, and the value is 40 there. Okay, so that is why your value is 40 here. And upper bound, if you substitute all the values, you are getting 70. So what we have to do, you have to, yeah, you have to again construct the partially, you have to construct the tree. Okay, so how you are going to do? So here this is not feasible, and here we are expanding here this one without 2. This is I think, yeah. Okay, so here, hmm. Here we have expanded this because this is W is equal to 11. It is not visible. Why it is not feasible? Because W is equal to 11, which is more than 10. So we are stopping it here. This becomes infeasible. That is the non-promising node it becomes. Okay, so here we are expanding this. Now what we have to do? We have to consider 4 and 2. Okay, so every time it is not expanding this. Previous node also we need to consider. This is 60 and this is 70. Which one will be chosen? This will be chosen because we are going to consider the upper bound, right? Okay, so next this has to be expanded. Next, item number 3, and V4 by W4 is equal to 4. Okay, so with including item this 3, so what is the weight? The third item's weight is 5, and the weight so far is 4. So the total weight becomes 9, and V is equal to, it is 40, and the value of the item 3 is 25. So the total value will become 65 here. Okay, and M minus W is, M is equal to 10, and the weight of this total weight so far is 9, so it becomes 1 here. Then if you substitute in the upper bound, you will be getting 69, and without item using the item 3, what will happen? W will be remaining same, and the V is remaining same, and M minus W is, M is 10, M is 10 here, and what is the weight so far? 4. So M 10 minus 4 is equal to 6. So if you substitute in that, you will get this upper bound as 64. Okay, then expand as usual, expand the tree here. Okay, if you expand the tree, you will be getting here the with the 3 and without 3. With the 3, this is UB is equal to 69, this is 64. So now consider 2, 5 and 6. So if you are considering 2, 5, if you consider 3 also, no problem, because it is not promising, we can also leave that. That is not a problem if you consider 2, 5, 3 and 6, right? Okay, so which is the promising node? This will become promising node. So next is item number 4. I is equal to 4. Okay, but V5 by W5, it is nothing, right? So just leave it. Next, with including item, what will happen here? This is item is equal to the weight so far will be here 9, plus next items, fourth item's weight is 3, so it is 12. So it is not feasible because it is more than 10. What is 10 there? Capacity of the knapsack. So it is not feasible. But without item 4, what will happen? So W is equal to, because you are not including the item 4, so that's weight is 0. And what is the item weight so far? Here it will be, here it will be 9 so far here. Okay, then after that value also 65 you have to consider. The value of the fourth item you are not going to consider because we are not including that, right? So M minus W is equal to 10 minus, what is the weight so far? 9, it becomes 1. Then upper bound will be 65. Then if we expand, after expanding that, what will you be getting here? So this will be UB is equal to 65 because this is not feasible and we are already exhausted all the items. So now we have to stop it. Now, how do you know that this will be the solution? How do you know that? I mean, here 60, 64 and 65, right? So this is maximum. So how do we find what are the items we have chosen? We have to follow this path, right? We have to follow this path. Okay, one second, I'll clear this first. Okay, yeah, now I can. Okay. So now, because here this is a solution, how do you reach this path? So from here to here, here, and here. And here, including with 1, we are following this path, which is with 1. That means 1 is included. And here we are following this path. This is without 2. That means it is 0. We are not including that item 2 here. And here with 3, that means third item is included. And without 4, the fourth item is not included. So if you are writing in the form of the solution vector, we can write, since 4 items are there, the first one is included, make it as 1, and the second one is not included, make it as 0, and the third one is included, make it as 1, and the fourth one is not included, make it as 0. Can also be a solution. Otherwise, whatever the items you are including, you can include those items in the solution vector like this. Any of this, if you write, that will be proper only. I hope you understood this. If you have any questions and queries, you can send me through WhatsApp. Thank you.